Well, hi everybody. In this session, I'm going to derive fluxes in conservation form. Well, as you know, Euler equations in 2D are in this form. U is the conserved variables, F and G are the fluxes, as stated here. Any of these have four elements. For example, for U, density and momentum in x direction, momentum in y direction, and the energy content of a fluid uh, confined in a control volume in space, in 2D space. And as for the fluxes, the elements are as I have written here. Well, if we name the elements, for example, the first element of U is rho, the second one is rho multiplied by U, and so on. And for F, the flux in x direction, we have the elements just like these. And for G, as you can see, these are the elements, and if we put them in order and number them, this is the form. Okay, if we are going to state flux elements in fact, we are going to describe and we are going to derive the flux elements in conserved variables. For example, as you can see here, the first element of F is rho U, okay? F1 is rho U. And as you can see here, the second element of U is rho U again. So very simply, you can write the first element of F is equal to the second element of U. So F1 equals U2. Okay? We are going to write any of the flux elements in description in U in conserved variables. For example, F4 as a function of U1, U2, U3, and U4. Or for example, G3 flux, the third element of G flux in Y direction. As a function, we are going to find the G function, for example, of variables U1, U2, U3, and U4. Okay, we found F1. Right now we are going for F2. As you can see, F2 is rho U2 plus P. And for the first term, rho U2, if you multiply this by rho and divide it again by rho, you have this shape of a mathematical operation, and you can put the power for all of it right here. Rho U equals U2. And rho equals the first element of U. As you can see, we have found the second element of flux F in terms of conserved variables. Okay? Excuse me. This was just for the first term. For the second term, we need to transform P into conserved variables again. In fact, we need to derive it. Okay, as you know, pressure with ideal gas law is rho RT, and again from thermodynamics, as you know, the total energy content of a fluid element is the internal energy of that fluid element plus the kinetic energy. Here V bar is the total velocity. It means, for example, as you can see here, from mathematical relations, you can relate V in power of 2 to the components of velocity components here, u2 plus v2. Okay. Again, from thermodynamics, we know that E, internal energy of a fluid element, is CVT, and for the CV, we have R over gamma minus 1. Gamma for air is 1.4. However, here we do not need the numerical value. It's just a constant. I want you to know that. Okay. We are searching for P. We want to know how can we transform P into conserved variables. Write it into conserved variables. Okay. Again, from here, P is rho RT, as you can see here again, and you can divide this equation by gamma minus 1, multiply and divide. Okay. So this part, as you can see, equals CV, this part. Okay, so we can write pressure is gamma minus 1 rho CVT. Okay, as you can see here from the above one, CVT equals internal energy here. So you can substitute gamma minus 1 rho E instead of CVT. Okay. Right now we can write it gamma minus 1 rho, and here just plus and minus the velocity, the total velocity, kinetic energy, the fluid element kinetic energy, plus this minus this. Okay, these two terms together are the total energy as was stated here. Okay, we formed it here. So we can write gamma minus 1 rho total energy, just multiply, minus, again, multiply this to this term, write it here. Okay, this one, rho ET, as you can see in before pages, is equal to U4. Okay, so we are going to find this term in terms of conserved variables. Okay. Well, as I was saying, just let's find this in terms of conserved variables right here. You know that this was like that, u2 plus v2. If you extract this velocity, it is like this. Okay, and you can write it here, just multiply by rho and divide by rho, multiply by rho and divide by rho. Okay, like this. And as you have seen, the conserved vector of the conserved variables vector, this is the u2 and this is u1, and for this one this is u3 and this is u1. Okay, just substitute. Now put this back in this relation here. For this we have gamma minus 1 and we have this in this form. Put them all together. So F2 is here plus this minus gamma minus 1 and here, just like that. Okay, just let's go over to the third element of flux F. The third element is rho uv. Just multiply by rho and divide by rho. The first term is u2 and the second term is u3. Denominator rho is just u1. So the third element of flux is just like this. Okay, just let's take over the last element of F, F4. F4, and by definition, is this. However, I will prove all these in a future video. For u, the x component of velocity, just multiply by rho and divide by rho. So you can, you know that this is u2 and the rho is u1. And here for rho et, as you know, rho et is just u4. Just play back the video and see the previous section. Rho et is u4 plus pressure, and we derived pressure in conserved form. Just substitute from the last section. It's like that, okay? And when you substitute for pressure, it's like that. And if you multiply this to u4, there would be a minus u4, which cancels this plus u4. So these two are cancelled out. Just there will be a gamma multiplied by u4 here. This is, as I said before, is u2 over u1. And for this one, just as substitute from pressure derivation, just here. And that's all. As you can see, F4 has been written in conserved form. All the variables are the conserved ones, and gamma is a constant value, okay? And this was just for flux in x direction. In fact, f flux, the vector f. If we want to do it for g, you can just do some simple operations like the ones I showed here. If you do that, you will see that g1, g2, g3, and g4 are all stated in conservation form like this, okay? In future CFD videos that I promise I will make them for you, this way of representation, this conservation representation of fluxes is very useful in some CFD techniques. I will show that to you in future. I hope it's near future. I hope you safety and health with joy, of course. Goodbye.